Hello, and welcome to my YouTube channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This video is one in a playlist on probability distributions. The playlist is planned to include a three-part series on distributions as a whole, plus individual videos on 9 different types of distributions, as well as several on the properties of distributions. See statisticsfromatoz.com/videos for the latest status of this work. As usual in the book and in these videos, we'll start by going quickly through a list of keys to understanding, or KTUs. This is to give you the overall picture of the concept on one page. And then we'll go into detailed explanations of each of the keys. For this video, there are 4 KTUs. The first key to understanding tells us that the values which comprise a sampling distribution are not individual data values, but are statistics, for example, the means, of samples. KTU number 2 says the samples must all be of the same size and must be taken with replacement from one population or process. The third key to understanding tells us that if the statistic comprising the sampling distribution is the mean or a proportion, the central limit theorem applies. And the fourth key to understanding tells us that the standard error is the standard deviation of the sampling distribution. And here on one page are all 4 keys to understanding the concept of sampling distribution. You may wish to pause the video at this point and read them all together. As we'll see, the sampling distribution is different from all the other distributions we've covered in the book and in these videos. Its primary value is the role it plays in the concepts of central limit theorem and standard error, which are covered in KTUs number 3 and 4. Okay, now let's take a more detailed look at each key to understanding. KTU number 1 says, the values which comprise a sampling distribution are not individual data values, but are statistics. For example, the means of samples. We are all familiar with probability distributions of data values, for example, the normal and binomial distributions. If we have a small data set, we can portray its distribution with a dot plot like this one. Here, each dot represents one data value. We see that there are 3 data points with a value of x equals 12, 2 with a value of x equals 13, 6 with a value of 14, and so on. And here is a visual representation of a sampling distribution similar to the dot plot. It is not intended to be a precise representation of a data set, but to give a visual illustration of the concept of sampling distribution. Instead of dots representing individual data points as in the dot plot, we have X-bar symbols representing means of samples. Each individual X-bar symbol represents a statistic, in this case the mean, of a different sample. A statistic is a numerical property of a sample. Examples are the mean, the range, standard deviation, variance, proportion, and so on. Each symbol in this graphic represents one sample and the statistic which describes it, its means. We can see that this distribution of the sample means has its own mean and that it is in the units of the data. KTU number 2 gives us the 3 requirements for the samples. They must all be of the same size, n. They must all be from one population or process, and the samples must be taken with replacement. To illustrate the concept of sampling with replacement, let's say we're doing a study in a small lake to determine the proportion of lake trout. Each trial consists of catching and identifying one fish. If it's a lake trout, we count 1 yes. If we catch a lake trout and then throw it back in before trying to catch the next fish, that is called sampling with replacement. So each time we drop our line to catch a fish, which is a trial, the probability of catching a lake trout remains the same, because the total fish population and the total lake population does not change if we replace the fish with each time we catch one. It would change if we did not sample with replacement. So the probability of each trial does not depend on the outcomes of any other trial, and the trials are independent of each other. By the way, as you may or may not recall, sampling with replacement is a requirement for a binomial experiment. This KTU and the next one are about the two main uses for the sampling distribution. The central limit theorem says that even if the data are not normally distributed, the sampling distribution of the means, or the sampling distributions of the proportions of the data, approach the normal distribution as the sample size n increases. N is the number of individual data points in each sample. It is not the number of samples taken. As n grows larger, the distribution of the means of the samples approaches a normal distribution more closely. For n greater than or equal to 30, the approximation will be very close, and some people say that there is no reason to go any higher than 30 for the sample size. In fact, for use with control charts, sample sizes as low as 4 have been used. The central limit theorem, CLT, is a powerful concept which helps us perform statistical analyses on any population or process, no matter the underlying shape of data, even weird shapes like these shown. We just take samples of data with replacement and calculate the means or proportions for those samples to get the sampling distribution. For more on the central limit theorem, please see my video on the normal distribution. The second major use for the sampling distribution is in defining the concept of standard error. Standard error is defined as the standard deviation of the sampling distribution. The concept of standard error will be described in more detail in a future video. To a considerable extent, standard error plays a behind-the-scenes role in statistics. It is used more frequently as an interim step in calculations or as a component of formulas than it is as a quoted statistic in its own right. Now, experts disagree on whether it is important to understand standard error as a separate concept. It is an abstract concept and it can be confusing. There are different formulas for different uses of the standard error. Here we show 3. For the standard error of the mean, SEM, for the standard error of the difference between two means, and for the standard error of the proportion. It may help to compare the sampling distribution with the probability distribution with which we are more familiar. These are data distributions such as the normal, the binomial, the exponential, etc. The average data value in a probability distribution is called the mean. For a sampling distribution of the mean, it is called the expected value of the mean. This is because it is the same as the population mean. As we've said, the standard deviation of the sampling distribution is called the standard error. And for both, the mean and standard deviation are expressed in units of the data values. And here again, on one page, are the 4 keys to understanding the concept of sampling distribution. Okay, that concludes our clarification of the concept of sampling distribution. If you liked this video, please remember to press the thumbs up like button on your screen below. Now, I'll be making more videos of some or most of the 60+ concepts in the book if folks like you tell me more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatoz.com has a listing of available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you will find interesting, like a Statistics Tip of the Week series, as well as posts showing that you are not alone if you're confused by statistics. I'll also be posting on the Facebook page, Statistics from A to Z, and on Twitter as @StatsA to Z.